were not associated with any polynomial of fixed degree with a finite number of terms. Beyond the algebraic functions lay the transcendental functions. The infinitesimal calculus and the notion and methods associated with differential equations allowed for the exploration of these functions by Leibniz, the Bernoulli's, Euler, and Lagrange inter alia, in conjunction with the nascent discipline of Newtonian mechanics. This set the stage for Gauss's work, which included the flowering complex analysis based on the insight that the Euclidean plane provides a good geometric model for the complex number system. Gauss also revisited the ancient Chinese remainder theorem with a fresh conceptualization called the quadratic reciprocity theorem, which explained for the first time why congruences, especially congruences precipitated by prime numbers, lie at the heart of number theory. So I've been using two sets of textbooks, Froelich and Taylor, and the textbook that I just mentioned earlier in vehicle parts. Froelich and Taylor begin their textbook, Algebraic Number Theory, really begin at page 1, with a nice example of ampliative reasoning where a problem is carried up into a broader context and then resituated. Exactly the same problem shows up at the beginning of Number Theory 1, authored by Cato et al. The problem was first articulated by Fermat in the 7th of the 48 comments he left in the margin of his copy of Arithmetica, published posthumously by his son. The context for this result was Fermat's study of right triangles in relation to prime numbers. Studying the triplets of integers that satisfy the equation x squared plus y squared equals c squared, he noted that the length of the hypotenuse in each case was a prime number congruent to 1, mod 4, and was never a prime number congruent to 3, mod 4. He generalized this observation to the claim that if p is a prime number congruent to 1 mod 4, then there exists a right triangle with integer sides such that the length of the hypotenuse is p. Conversely, no such right triangle exists for any prime number p congruent to 3 mod 4. To say that two integers are equivalent mod n, as we all know, means that if they were divided by n an integer, the remainder in both cases would be the same. So 5, 13, and 17, for example, are equivalent mod 4. It's easy to see that every integer n thus divides up the infinite set of integers into n equivalence classes. There it is, which can then be themselves treated as elements of a set. Indeed, they form a finite group, and if n is prime, they form a finite field. This sorting of the integers by modding out a subgroup provides useful information, especially when n is prime, or the power of prime. Note that whereas the concept of an integer has an obvious geometrical interpretation, a certain line length, the concepts of a prime number and of congruence do not. Here, Fermat brings these concepts into productive association for the first time. This result led Fermat to ask, under what condition an odd prime p may be written as the sum of two squares, equals x squared plus y squared, where x and y are integers, and under what condition it may not be so written. Notice that this equation has no obvious geometrical significance, though it is clearly formally or rather algebraically related to the equation p squared equals x squared plus y squared. Fermat asserted that the first condition is p is congruent to 1 mod 4. The second is p is congruent to 3 mod 4 in his two squares theorem. Fermat asserted this claim without proof. Euler proved it about 100 years later in the formal and rather unilluminating method of infinite descent. But the key explanatory insight is that a prime number p congruent to 1 mod 4 loses its irreducibility as a prime number in the ring Zi of Gaussian integers in the field Qi, while a prime number p congruent to 3 mod 4 remains prime. This claim requires a bit of elaboration. The field Qi is the algebraic extension of the field of rational numbers Q, obtained by adjoining the square root of negative 1 to the rationals. Its elements are of the form a plus bi, where a and b are rational, which can be added, subtracted, and multiplied in the usual ways of arithmetic, augmented by the equation I squared equals -1. And a bit of computation shows that every element is invertible. Within this field, Qi, we can locate the analog of the integers within Q. It is Zi, the Gaussian integers, whose elements are of the form a plus bi, where a and b are integers. Like Z, Zi enjoys unique prime decomposition, but its primes are different from those of Z. And instead of 2 units, it has 4. To be a prime in Zi, a plus b must satisfy certain conditions. There they are. Either a is 0 and b is a prime in Z and is congruent to 3 mod 4, or b is 0 and a is a prime in Z and is congruent to 3 mod 4. Or neither a nor b are 0 and a squared plus b squared is a prime in Z and is not congruent to 3 mod 4. If we return to Fermat's two-square theorem, we note that 5, 13, and 17 cease to be prime in Zi and may be factored here, whereas 7, 11, and 19 remain prime. So there are 5, 13, and 17 with their factorization, and whoa, look! They're the sum of 2 squares. It's right there. That is an intuition. I don't know what it is. Richard Dedekind, using a result of Lagrange, offered a proof that exploits this insight in 1894. There is a version of its presentation in Froelich and Taylor. I don't know that it's worth going through that whole proof. You can do that yourself, since our time is limited. So, what I want to point out to you, and you can see it in the paper in front of you, is that we do some reasoning about congruences and the constraints put on numbers by congruences. And right in the middle of the proof, we go from Q up to Qi. We do some reasoning. Well, from Z really up to Zi. We do some reasoning up there. See where it says we go upstairs to Zi? And we see that P as we go up and then we come down, that P is of the form P equals x plus Iy, x minus Iy. It has to be of that form by the constraints put on it by the situation. And when we bring it back downstairs by applying the norm, we see that p squared equals x squared plus y squared times x squared plus y squared, which means that p is x squared plus y squared. This problem-solving strategy sets the concept involved in its problem number theory into novel proximity with a variety of concepts. First, of course, it relates the integers to the complex numbers. Since Gauss was the first to suggest using the Euclidean plane as a model for C, the units are then modeled by the square with endpoints 0, 1, I0, 0, minus 1, minus I0. This suggests a generalization which models the set of nth roots of unity as vertices of regular n polygons centered at 0, 0. Along with a generalization from Qi to other algebraic fields called cyclotomic fields, where an nth root of unity is adjoined to Q. These roots of unity suggest the notion of symmetry when they are interpreted as regular polygons. And though it's a little more complicated probably than I think, there is a root there to get law theory, but we will jump over that. The field, so that's the first association of concepts. The second is the field Qi is also a vector space. A vector space is not merely an abstract structure, it is a toolkit of related concepts. Basis, norm, inner product, vector, scalar, eigenvector, eigenvalue, and of course dimension. The notion of norm played an important role in the proof just given. And finally, it brings in again the notion of congruence, which plays a central role in the proof. Congruence mod 4. And we have seen that the key to the latter problem solution is the insight that some primes in Q remain prime in Qi, and some primes decompose into factors which are prime in Qi. And that this sorting must be carried out by looking at the primes in terms of which congruous class, mod 4, they belong to. Now, what follows in the next paragraph is another set of associations. You look a little bit further down the path, and you see that the Galois group of Q, zeta, n over Q is isomorphic to the multiplicative group of the finite division group C over nz. There also exists a one-to-one correspondence between subfields of Q, zeta n, and subgroups of the Galois group Q, zeta n over Q. These correspondences allow us to find patterns linking the decomposition, factoring of prime numbers in cyclotomic fields to specific congruences. For example, a prime decomposes in Q zeta 7 if it is congruent to 1 mod 7. A prime decomposes in Q zeta 5 if it's congruent to 1 mod 5. And here's the theorem that generalizes these facts. Let n be a natural number. Suppose that a subfield L of Q zeta n corresponds to a subgroup H of C and Z, the multiplicative group, isomorphic to Q zeta n over Q. Then for any prime number P, not dividing n, we can prove that P is totally decomposed in L if and only if P mod n is an element of H. The way a prime number P decomposes in a subfield of the cyclotomic field Q zeta n is determined by P mod n. These kinds of patterns relating inner to outer, that is the outer to inner, that is the way that the integers can be embedded in algebraic number fields to the internal fine structure of the integers, revealed by congruences, lead eventually to class field theory. As Cato writes rather poetically, in chapter 10 of his co-authored Number Theory 2, he says, in a fairy tale, sceneries far away from home may be seen in the magic mirror. How many abelian extensions are there over a global or local field K? What happens in such abelian extensions? These outdoor sceneries of K are reflected in the indoor mirror of K, that is the multiplicative group or the Edel class group of K. This is the main content of what class field theory is. Now, here we are at 12:15. What's in the next section is a similar example where the algebraic field is Q with the square root of 2 adjoined. And what's in the next section after that is a relatively basic example from analytic number theory. These two examples are really algebraic number theory. There's an example from analytic number theory. So let me just kind of sketch what's in section 3.
Emily, could I
Yes.
interrupt?
Or we can.
I was wondering if you could summarize from a more philosophical point of view than a mathematical point of view what it is you're saying, because there's a lot of number theory.
Yep.
It would help me if you could kind of distill the
Well,
non-mathematical point.
so what I'm trying to show is in these examples, the fact that you have to go upstairs to solve a problem, and that the going upstairs involves not only a new entity, and a highly non-trivial entity, that is, cyclotomic algebraic fields and quadratic algebraic fields, in a certain sense, are well understood. If you go beyond that, they lose many of their nice properties, and it's like going up to third and fourth order logics. They lose their nice properties. You can wave your hands and point to them, but they're really not very well understood. And another way of putting this is, all of those algebraic number fields, in a sense, are sitting inside the completion, the algebraic completion of the rationals. But what exactly they are and what exactly their properties are highly non-trivial and very difficult to investigate. So just because you can write formally Q with a line over it does not mean that you understand the fine structure of Q. Okay, so the hard work of investigating algebraic number fields, for example, if you say that that could be deduced from those axioms that Enterton gives, is silly. Now, I understand that there is a way to finish this, which is up here in what you can't read. You can say something like, oh, with the expressive order of first order predicate logic and these nice axioms, we can write works that capture all the sets in the arithmetic hierarchy. Right? So all the things that we need to invoke are sitting there in the arithmetic hierarchy. That's like saying they're all sitting there in the completion of Q. But that doesn't give us the concepts we need in order to investigate them. Silence.
I'm happy.
So that's, what I really want to do, restate your question again. What did you want to do?
No, I wanted to have you say what you said. I'm quite happy that I now have a clearer idea, but there are other people in the room. I have a clearer idea of how you're proceeding, and you're saying that the way mathematicians work and the way they construct theories is really not captured by some claim that it's all expressible in a formalized language.
Right, because what's lacking here,
And therefore the reduction to a formalized language and the expression of philosophy of mathematics within some theory of sets is inadequate to explain what mathematicians do.
because sets are just sets, and wolves aren't just wolves, and they're really different from numbers. And you need a highly developed set, you need a highly developed collection of very specific concepts in order to get anywhere, let's say here with number theory. And you can't elicit them from the vocabulary of set theory. You wouldn't be using that. Here's an example of an argument that comes a little later in the paper, which is the Padic numbers. The Padic numbers and Padic representations play a really, really important role in late 20th century number theory, and they're, along with L functions, they're kind of the hinge in which the proof moves. So, what are Padic numbers? Well, I like Cato's description, which is, if you think of congruence mod p as sorting the integers into rooms, then congruence mod p squared sorts them into a different collection of rooms. Congruence mod p cubed sorts them into yet another set of rooms. If you have two numbers that stay in the same room throughout all those congruences, we say those are close together. And that is the sort of the basic idea under the completion. It's a very, very novel notion of closeness, which gives you an analog of completion, which works really very nicely, so that the Padic numbers for some P is a completion of Q, just as R is a completion of Q. But you only get that with the development of the notion of congruences, allied with the development of group theory in a certain specific way, and with the development of topology, and a generalization of the notion of closeness and difference, which is so abstract or so general that it can be used to formulate this novel notion of closeness, which works for the integers. Who would imagine that you could treat the integers that way? Because look at the integers. There they are, they're all a unit away from each other. Who would think that there would be any interesting topology there? Right? But if you take topology and you take the notion of congruence and you put them together in number theory, it works. You know, and I'm sorry, but you can't get there from here. Yes, ma'am.
So do you want to say what that has to do with values?
Yeah, is that if you look at how mathematicians offer explanations, they offer explanations in a way that is essentially ampliative in many, many cases. And explanation is, in mathematics, is the way in which we render mathematics intelligible. In other words, if you look at Fermat and these sort of odd facts about numbers, or even if you look at the first formulation, like if you read the first formulation that Gauss gives of the quadratic reciprocity theorem, you go, oh, well that's weird. You know, that's interesting, but it's just this kind of odd fact that's sitting there. And that's not, mathematicians can't rest satisfied with that. Mathematics requires an explanation. So, you know, it's increasing the intelligibility of mathematics, and intelligibility, I said in my Spinozan fashion, is the great value, both metaphysically, I think, for human existence and for mathematics.
But how do you link this with, I mean, you mentioned at the beginning a very, very nice, you said a very nice sentence, I'm not a Platonist, but the fact that mathematics has its own objects and so on. So you made afterwards a purely Platonistic statement about the fact that mathematics has its own objects.
No, it's, that's not Platonist.
And no, that just let me say the question. And my question is, doesn't it depend, so this intelligibility on the reader, on the audience? So I mean, we from our side cannot really judge how the contemporaries of Gauss or of Descartes or whoever have read these things. So isn't it depending on habits, on reading habits, on the skills how to deal with this kind of presentations or representations, or is it purely algorithm? So is it purely formulas? Is it independent of that?
Okay, I think you've really asked me 2 or 3 questions. One of the problems with the way in which predicate logic has dominated philosophy of mathematics in the 20th century is really the fact that it is first order predicate logic, for most of the interesting cases, is never categorical, and it is a logic of propositions. So what gets lost there is the fact that mathematics is about mathematical things, and that the mathematical things are really different kinds of things, and that mathematicians attend to the peculiarities of the things that they study when they study them. Now, if you look at the practice of, let's say, a late 20th century mathematician, you'd say, it's all abstract structures. But it isn't, because what they do is they take for granted the peculiar the peculiar features of the heterogeneous objects that they know all about because they've already studied them. And then they have this habit, for example, treating some numbers like the topological space and then seeing where you can go with them. Right? So I'm trying to explain to you why I'm not a Platonist. I'm a person who attends to mathematical practice. Right? And the second part of your question was?
The reader.
Oh yeah, so rigor.
Not the
Well,
reader,
I mean-
not rigor, but the reader or the audience.
Right,
The
okay.
different
No,
type
no.
of audience.
So in different historical eras, what counts as rigor and how we accept a proof as a proof varies some. You can be Henk Boos, and you can go back to the 17th century and you can look very, very carefully at the standards of proof, and you can give a historical account of the difference in the conception of rigor then, if you want, and we can make it pretty clear to everybody. So I think that's a problem that can be solved. That's a philosophy. You can say, yes, there is some variation. Nonetheless, you can read a Greek proof of the Pythagorean theorem, at the end of book 1 of Euclid, and go, that works. So there's some variation, but, there's also very strong continuity. How about the last two questions, because I think we're almost out of time.
Okay, I'm Colin, I'm Brennan's PhD student. You said that you have to go upstairs to solve problems. Do you think there's a general way how to do this? How to go upstairs? Or is this in cases? That
No, of course not.
there's no general way. I mean, there's no good way
No,
to...
because a lot of times, in order to go upstairs, you have to create new definitions, like the definition of a norm. You have to create new definitions that will give you the scaffolding you need. Sometimes you need new definitions to go up, and you need new definitions to come down, so that going upstairs is itself inherently ampliative. Not only is the upstairs not in the downstairs, but the difficulty of controlling going up and going down so that it will be sufficiently rigorous and you can have proofs afterwards often requires you to create extra structure, extra things.
But so creating new definitions is not a good way to go upstairs.
No, you have to do that. You have to do some of that. For example, creating the definition of a norm. Or the definition of a vector space.
Yeah, I have just a simple remark, which is that we often say, or